the relation between trading strategies and excursions, representation of trading strategy in terms of excursions of trading say signals or price excursions. Then we derived some pathwise results regarding the properties of excursions of irregular paths in relation with local time. Then we looked at the case where the underlying process is a Markov process, and we saw that Ito's theory of excursions gives a very rich set of tools to study the probabilistic properties of excursions for this Markov case. And then we gave some parametric examples, namely Brownian motion and the Ornstein-Uhlenbeck process, which are very widely used models in finance to model trading state signals. But what we saw yesterday is that these Brownian motion and Ornstein-Uhlenbeck processes, although they're very tractable and nice, they do not seem to correctly represent the properties of excursions of processes encountered in financial applications like prices or trading signals. In particular, what we saw yesterday in detail is that two things really matter for the representation of the risk and return of these trading strategies we are looking at. These two things are the duration of the delta excursions, which tell you how frequently you will trade, and then the amplitude of the excursions, which tell you something about the risk of the strategy. So at least you want that your model correctly represents the distribution of the excursion amplitudes and the distribution of the durations of the excursions. But we saw that the Ornstein-Uhlenbeck model or the Brownian motion do not correctly represent what we see in the data. So this leads to inaccurate representation of the risk and return of the trading strategy. So it's not very good. So it means that these models may be good for other things, but they're not actually good for analyzing the risk and return of these strategies. And to show you, let me just show you an example of what I'm talking about. So this is, let me show you just a graph from yesterday's talk. This graph, I think, is the most interesting. So this graph shows you for one of the data examples that we saw yesterday, the SDH-SH pairs trading application. So we saw, we fitted the Ornstein-Uhlenbeck model. And what we saw is that if you compare the amplitude of the excursions of the data with the amplitude of the excursions of the Ornstein-Uhlenbeck, so the Ornstein-Uhlenbeck has this distribution, the orange line, and then the data has this blue distribution. And the green one would correspond to the distribution of amplitudes for Brownian motion. So what we saw is that it seems to have a hybrid behavior, the data. So for small excursions, it behaves like an OU process, Ornstein-Uhlenbeck with mean reversion. But for large excursion, when you go away from zero, it seems to just, there's no mean reversion and it behaves like a Brownian motion. So it seems like a regime switching thing. So it's certainly not like any of these models taken alone. Okay. So what we want to do today is see how we can build models which capture these features in particular, but more generally, if I have information on the excursions of a process, say excursion amplitudes, durations, or the joint distributions of these, or more detailed information, can I build a stochastic process which has the correct properties of excursions? So I will give, so what we saw in the previous lectures is you start from a path or you start from a process and you decompose it into delta excursions. And there's a unique decomposition. But now we're going to use this decomposition in the opposite direction. We're going to use this decomposition as a way for constructing processes whose delta excursions have the properties that we want. So we're going to choose a family of curves, which are delta excursions, which go from 0 to delta to 0, which have the right properties in terms of amplitude, duration, and we're going to paste them together to make a process. And if we do it in the right way, then we'll get a well-defined process which will have the right properties for excursions. So I'm going to propose two different constructions for this. So the idea is constructing a process from its excursions instead of studying the excursions of a process, which is the classical approach. So I'm going to propose two methods for doing this, a parametric method and a non-parametric method. And these constructions will lead to new classes of stochastic processes with desirable properties for the excursions, and it will lead to new examples of stochastic processes in general. And we will see that this way of constructing stochastic models, first of all, it's very amenable to computations because we define the processes in terms of global objects, not infinitesimal objects. And then it will be easy to simulate or compute once we construct the process in this way. So that you will see why I say this. Okay, so first let me get into the first method for constructing a process from excursions, and that's what I call Markovian pasting or Markovian concatenation. So, so here's the statement. So we saw that if you take a Markov process and you decompose it into delta excursions, the strong Markov property implies that the delta excursions are IID. So it's a decomposition of the Markov process into an IID sum, IID concatenation of pieces. And now we're going to do the opposite. I'm going to construct the Markov process by starting from a family of delta excursions, which I construct independently. And then I'm going to paste them together. I'm going to join them together and when they reach zero. So here's how. So this is one example, and then you can understand that you can generalize this construction. So let's say, to construct a delta excursion, so a delta excursion is a path which goes from 0 to delta and then from delta to 0. So I need to model what happens inside the delta excursion. So I need to specify the law of the process when it goes from 0 to delta, and I need to specify the law of the process when it goes from delta to 0. I need to specify these two pieces. Then I get the law of one delta excursion, and then I do IID copies of this, and then I paste them together. That's the idea. So, and to do this, I'm going to give myself the freedom to choose two Markov processes, S plus and S minus. S plus will denote the dynamics when I'm going from 0 to delta, when I'm going up, and S minus is going to denote the dynamics when I'm going down from delta to 0. They can be different. For example, think of S plus is some Ornstein-Uhlenbeck process with some parameters. S minus is an Ornstein-Uhlenbeck process with other parameters. Or if you think of the data example I just showed you, S plus can be an Ornstein-Uhlenbeck process and S minus can be a Brownian motion, or it can be any other Markov process. So
excuse me, Rama. The slides appear a bit small. Could you please?
Oh, sorry. Is it better now?
Oh, yes, much more.
Okay. Yeah, so I'm going to choose a pair of Markov processes, S plus and S minus. And the only assumption I need to make is that these processes, they go from 0 to delta and from delta to 0 with probability 1. So more precisely, I want S plus to go from 0 to delta, and I want S minus to go from delta to 0. So I want it, if I start it at 0, I want it to go from 0 to minus delta. So when I add them, they go back to 0. So this is the only assumption, that the probability of reaching delta from 0 is 1, and the probability of reaching minus delta from 0 for S minus is 1. So you always reach these levels in a finite time. So this way you don't have trajectories that get stuck in one of the two and never reach the other. I mean, you can still do the construction, but it's less interesting. So now what I'm going to do is I'm going to construct one delta excursion by pasting S plus and S minus together at the first hitting time of delta. So what does it mean? It means I start from time 0, S plus starts from 0. So this is the assumption here. S plus of 0 is 0 with probability 1. I start from 0. I go up, I let it evolve, and at some point it will reach delta. This is the hitting time T delta of S plus. My notation is, this is the notation for the hitting time of delta, the first hitting time of delta. When I reach delta, then I stop S plus, and then I run the process according to S minus. I change parameters, and I run according to S minus until I reach 0, and then I stop. So this is going to be, also I paste them together at delta, and I stop when I reach 0. This piece, I'm going to call it E. This is one delta excursion. And this defines completely the law of the delta excursion. The law of the delta excursion is the law of a process which coincides with S plus up to the first hitting time of delta, and then coincides with S minus from that point onwards until it reaches 0. So this law defines a probability measure, pi delta, on the space of delta excursions. And now I make independent copies of this. I take a family of IID variables with this law pi delta, EK. So K will be the kth delta excursion of my process. And then I will paste them together. So I call delta K the lifetime up to the lifetime of the kth delta excursion. And so I paste them together with this with the usual pasting formula. I just add them up to, on the interval, which is the lifetime of EK, it's the process X is equal to EK, and then you move to the net X1 and so on. So this is the concatenation of these delta excursions. And I claim that this construction, so the existence is shown here. It shows you how to construct it. And I claim that this process is unique in law because this construction completely defines the law of XT. And it's delta excursions. If I now take XT and decompose it into delta excursions, I get exactly the EK because of the uniqueness of the decomposition in delta excursions. So I have constructed in this way a process X whose delta excursions are independent with a given law pi delta. And I can construct the law pi delta by choosing appropriately the ingredients, the up and down ingredients, S plus and S minus. Okay, and in fact, the law pi delta can be recovered from X in the following way. The law of each piece EK is exactly the law of the process X stopped at the end of its first delta excursion. And this is exactly the decomposition of X into delta excursions. Okay, so this is exactly the converse of what we saw when we saw Ito's theory. Ito tells us how to decompose a process into excursions, and then we tweaked it a little bit to get the decomposition into delta excursions. We saw that this is IID decomposition, and now I do the opposite. I construct a valid law on the space of delta excursions by doing this, and then I just take IID copies and stick them together, paste them together to get a process. And this is a way of constructing the process. It's not the usual way you do it. It's not via SDE or a generator, but it gives you the unique law of a process. Okay, so now can we describe this process X constructed in this way? First of all, I need to prove that this is a valid construction, and then can I characterize this process X? What is it? What do I know about this process? It turns out that, in fact, we can characterize it, and so you can think of it in the following way. I'm going to describe a little bit more detailed mathematics in the next few slides, but you can think of it in the following way. So X is composed of pieces, which are these delta excursions. Each delta excursion starts at some hitting time of 0 and stops at the hitting time of delta, or it starts at hitting time of delta and stops at hitting time of 0. And when you're in the up phase, it evolves according to S plus, and when in the down phase, it evolves according to S minus. So you can describe, now X itself is not a Markov process, because as you can see, there's some path dependence here, because I can be at the same point during the up phase and the down phase, but the transition probabilities will be different. If I say a point X is between 0 and delta, if I visit this point during the up phase, the transition probabilities from that point will be determined according to S plus. Whereas if I visit that point during the down phase, the transition probabilities will be determined according to S minus. So it means that the transition probabilities do not depend just on the starting point, but also on which phase I'm in, plus or minus. So there is some path dependence here. But the path dependence is easy because there's just, I need to know just one extra variable, whether I'm in the plus up phase or down phase. So it means that I can just augment my state space with one more dimension, which can take two values, plus or minus. And then on this augmented state space, I'm going to construct a Markov process, a classical Markov process. And then my process X will be the first component of this Markov process. So the first component will be the position, and the second component will be the up or down phase, the regime, if you want. And then I will show that the thing I want, X, is the projection of this Markov process on its first component, the position. Okay, so how does this work? Well, you can think of it like this. So I have a Markov process evolving on the real line, but now I make two copies of the real line, plus and minus. Okay, I label one plus. So when I'm in the ascending phase, I'm here in the blue region. And when I'm in the descending phase, down phase, I'm in the green region. So, this is the first part of the delta excursion. This is the second part of the delta excursion. So the blue phase, it's the phase where I'm going from 0 to delta. Of course, I'm allowed to go below 0, but I'm not allowed to go above delta during the up phase, because as soon as I reach delta, the up phase finishes. So in the plus regime, I live on the minus infinity delta. I live below delta. So I start somewhere here. Say I start at 0, okay, and now I'm in the plus phase. So I'm going to evolve here. I'm going to go up, down, up, down, up, down. And at some point, I'm going to reach delta, and then the process transitions over to the minus phase. Then from this point onwards, I switch to S minus. Now it's the downward phase of the delta excursion. So I'm still at the position delta, but now I'm in phase minus. So in my state space, I switch from the point delta plus to the point delta minus. So this takes place with probability 1. The black arrow is with probability 1. Here I have some transition probability, but here I go, this transition from this point to this point is with probability 1. Then now I'm at the point delta, but now I start evolving according to the S minus dynamics. And again, I can go above delta or below delta. I can go up and down here until I reach B0. When I reach B0, then it's the end of the delta excursion. Now I start the next phase, which is the up phase of the next excursion. So again, when I reach 0 during the regime delta, then during the minus regime, I start here. So this transition is with probability 1. So it means I diffuse here, I reach here, up, I go here, then I diffuse in the green region, I reach here and go here, and I cycle like this. So you can guess that, you know, this we can construct this like a Markov process, but in this state space, which is a little bit complicated, but I'm going to write it down. But it's shown here in the figure. It's the green and the blue regions, and with the boundary that is given by these orange part. So the state space has a boundary that is given by the orange things. And I need to specify the state space properly, specify the generator and so on, but I'm going to show you the next one. Okay, so as you can see from this graph, the proof of the construction is the following. We're going to construct an auxiliary Markov process on this bigger state space such that, in fact, the delta excursions of X, which I'm interested in, correspond to the excursions of Y away from a certain point. And this point is going to be the point 0 plus. Okay. So, and as I showed you in the figure, to describe the transitions of X, there's path dependence in X. In addition to the current position, I need to know whether I'm in the blue or green phase, which we call plus or minus. Okay. So what we're going to construct is, in fact, a Markovian lifting of X. So it's a Markov process in a higher dimension on a large state space, a y1, y2, such that y1 is going to be X at the end, and y2 is going to be plus or minus. So what is the state space? Well, in the figure I showed you what it is, but it is this. So so you take minus infinity delta. This is in the up phase. During the up phase, before you reach delta from below, you're allowed to be anywhere below delta. And this is associated with the up phase. It's a plus. And then in the down phase, you're allowed to be anywhere above 0. You stop at the first time you hit 0. So it's 0 infinity times minus. And in general, you can restrict it to an interval subset of these. So I include it's called I here. So I is the interval, is the natural state space for the Markov processes S plus and S minus. Okay, so we're going to construct the Markov process on this large state space, and then we're going to just take the first component. It'll satisfy the requirements we want. So how do we construct this? Well, there are two ways to construct this. I'm going to do it via the generator. So I'm going to specify the generator, and then this is going to give me a unique Markov process on this state space. So what is the generator? Well, so the generator is going to tell us explicitly what happens at the boundaries, what happens inside each region, and so on. So remember, the ingredients are, I start from these two Markov processes, S plus and S minus. Let's assume that they live, S plus lives on minus infinity delta, and S minus lives on 0 infinity. But in general, they can live on a subinterval. It's fine. And well, the S plus has some generator, infinitesimal generator L plus. S minus has some infinitesimal generator L minus on, and I can use as domain the space of C2 functions. So think of diffusions here. I'm typically thinking of diffusions. But okay, so if I have a diffusion, then it has some generator which has a domain which is C2 functions. Okay. And okay, now I'm going to construct the generator for my bigger process from the generators L plus L minus. So the tricky thing is by defining the domain correctly. So the domain will be functions on this enlarged state space. I'm going to denote E plus the restriction to so this is, sorry, E plus is what I call the green region, E minus is what I call the blue region. So no, it's the opposite. E plus is the blue region, E minus is the green region. So when I'm living in the down phase, the minus phase, I'm living in the E minus. When I'm in the up phase, I'm evolving in E plus. So I take a function on the whole space, and when I'm in E plus, the process will evolve according to the generator L plus. So I want the restriction to E plus to be in the domain of the generator L plus. When I'm living in E minus, when I'm evolving in the minus phase, I'm in the domain of, I want the restriction of the function to be in the domain of E minus. So that's the first restriction. And then I have to pay attention to the boundary condition, what happens when I hit the boundary? Well, when I hit the boundary, what we said is that when I hit here, I transition with probability 1 here. And when I hit here, I transition with probability 1 here. So whatever is the value of my function here, I transport it here. And whatever the value of the function is here, I transport it here. So it means that I have the Dirichlet boundary conditions at these things. It means that so f minus is the value on the left, f plus is the value on the right. I need that these two values are equal at these 2 points, 0 and delta. That's it. That's it. And now I can define the generator of my bigger process. So the generator of my bigger process does the following thing. While I am in the plus phase, it behaves according to the generator L plus. While I am in the minus phase, I'm on the left, it behaves according to L minus. And then I have these junction conditions. It says that when I'm at the boundary, the value on the left is equal to the value on the right, and so on. That's it. And then what we can check is that if we define the process according to the transitions that I described here, the description I gave you with words, you can translate it into a description in terms of transition probability. So inside here, the transitions are determined by S plus, here by S minus, and then you have transition probability 1 here according to the black arrows. You can then show that if you define a process with such transition probabilities, it's a solution to the martingale problem for this enlarged generator. So it defines a Markov process with this generator. So this is done in the paper. I'm not going to go through the steps. It's a little bit heavy, but it's pretty straightforward. So this describes completely this Markov process Y on the enlarged state space. And what we want, but the process X is going to be just the first component of Y. This is, sorry, this is, I said it here, X will be equal to Y1, okay? And so I don't need the regime. So this construction shows you that to do this construction, we need to construct a Markov process on a bigger state space. The path dependence of the excursions is encoded in the second component of the space, the plus minus. And so X itself is not a Markov process. As I said, there's path dependence in the dynamics, but it is the projection of a Markov process in a slightly bigger state space. So Y is a Markov process, so it's easy to simulate or model or compute with. We have a generator, we have explicit characterization of the law, so it's not much more complicated. It's what people can call a regime switching model with two regimes. You can think of it as a regime switching diffusion with two regimes. In regime plus, you do you evolve according to some generator L plus. In regime minus, you evolve according to generator L minus. But in most the regime switching models, for example, encountered in econometrics, the regime switching is done according to some Markov chain. But here, the regime switching is endogenous. It's determined by the hitting times of the first component. So you switch from one regime to another at the hitting times at some sequence of hitting times of X. So it's entirely determined by X and not by another independent stochastic source. Okay, so this is the special property of this. It's a regime switching model where you do not need another source of noise. It's entirely determined by X, and that's it because it's constructed according to the excursions. And the transition probabilities of X are precisely given by the transition probabilities of the components S plus S minus, which we start with. So more precisely, X behaves like S plus during its excursions from 0 to delta. What does it mean? It means that if I start from 0 and I look at a time t plus h after the initial time, which at a time where I haven't reached that delta yet, so this time is smaller than the hitting time of delta, then the transition from t to t plus h is exactly given by the transition probabilities of s plus from 0 to between 0 and h. This is the precise statement. And second, x behaves like s minus starting from delta during its excursions from delta to 0. This is the minus regime, which means exactly the following. If I start from delta at some point t until I reach 0, the transition probabilities will coincide exactly with the transition probabilities of the process S minus between 0 and h. Okay, so these two equations completely describe the transition probabilities of x, although x is not Markov. Okay, because s plus and s minus are Markov. Okay, so you have a non-Markov process, but slightly more complicated than a Markov. Yet you have a precise description of the transition probabilities. You have a description of the generator of the Markovian lifting, so you can simulate and compute everything with this. Now, examples of this construction. Well, in this construction, I have two ingredients, S plus and S minus. I can choose any Markov process for S plus and S minus and paste them together. So here's an example, a model with asymmetric excursions. Let's say that I study my data, and as we saw in the graph that I showed you earlier, we conclude that, when the signal goes up from 0 to delta, it has some Ornstein-Uhlenbeck dynamics with some parameters, but when it comes back from delta to 0, it comes back much slower. And it has another dynamics, which I can also model with Ornstein-Uhlenbeck, but with different parameters, alpha minus, mu minus, gamma minus. Okay, can I build a process which has such asymmetric excursions? Answer is yes. You choose as S plus the law of an Ornstein-Uhlenbeck with these parameters. You choose as S minus the law of another Ornstein-Uhlenbeck with these parameters, and then you do the previous construction. So what you get is this. It's very nice to visualize here. So this is a process which evolves exactly according to our construction. So the blue parts evolve according to the Ornstein-Uhlenbeck with parameters alpha plus, mu plus, gamma plus. The blue parts are the plus phase. They always start at the hitting time of 0. So here's one example. I start at hitting time of 0. I evolve according to the blue dynamics until I reach delta. In this case, delta is equal to 0.5. And then I switch to the red dynamics. Now for the red part is path simulated according to the OU with alpha minus, mu minus, gamma minus. Then this continues until I reach 0 again. Then I start the blue, and then I start the red, and so on. So the path of this process will alternate between paths simulated according to one regime or the other regime. Inside each regime, it's a SDE with very well-known structure. You can use whatever the simulation method you want inside each phase. The only thing is that you switch parameters when you hit the 0. So it's like a SDE with discontinuous coefficients, which have an indicator of certain hitting times involved. Okay, but this discontinuity, these hitting times in the SDE coefficients make them path dependent. It sounds very complicated, but it's not very complicated, because as we saw, underlying this is a Markov process, which you can simulate very easily. So you just need to keep track of, compared to simulating the ordinary Ornstein-Uhlenbeck, you need to keep track of one more variable, which is the color. Are you in red or blue? And then you choose the parameters you simulate, and you switch from one to another. Very easy. So in this example, you see a sample path of such a construction. Delta is 0.5, so you switch when you hit 0 or 0.5. And the two parameters are this. For the blue phase, you have mean reversion 0.4. For the red phase, you have mean reversion 0.1, so it's a bit slower. Okay, so that's an example. This is an example of the construction we give in the theorem. And of course, you can use anything else. You can use OU, you can use any favorite Markov process you have for the blue and red. And that's an empirical question, what you want to model. So, so some of you may be familiar with a process which was constructed by, well, first by Ito and Makin and studied by Walsh. It's called Cubranian Motion. So Cubranian motion may be considered as a special case of this construction with delta equals 0. So here you have delta, so you switch when you reach delta. And in the construction of Ito and Makin, they say, okay, here's a funny process. Let's say you have a Brownian motion, which when it's above 0, it has some variance sigma 1 squared, and it's below 0, it has variance sigma 2 squared. Can you construct that? And Ito and Makin construct that. They say, well, you know, intuitively what it has to do is that it has to switch variances when you cross 0. So it means that each excursion will have a different variance according to its above or below 0. So they construct such a process. They call it Cubranian motion. It's studied a lot in queuing theory because it emerges as the limit of certain queuing systems. And here you can think of it as a generalization of that, but you can have more asymmetry here because of delta. So here I switch when I hit delta and 0. So delta and 0 can be different. So you can have a more complicated asymmetry here. But so it reminds you of the Cubranian motion construction, which is was studied by Walsh in great detail. Now, this process is already an interesting example because it's related to the data I showed you. The data I showed you shows that there is some asymmetry between the dynamics below some level delta and above the level delta. So for instance, if we look at the graph here that I showed you, it shows that there is a clear breaking point here. For excursions below this level, it behaves like an OU. For excursions above this level, it behaves like a Brownian motion. This construction gives you a way to build examples which do exactly that. Okay, you can choose as S minus a Brownian motion, and then you will get something like what we see in the data. Now, if you, well, you can say, well, you know, what's the big fuss? This is an OU in both phases. I can just take this data and model it with a single Ornstein-Uhlenbeck. Well, if you do that, and that's what you do in applications in finance, people model the signal with an Ornstein-Uhlenbeck all along the trajectory. They don't distinguish between what's it doing far from 0, close to 0, or up and down phase. Well, in this example, what we do is we take this process. So remember, there are two mean reversion speeds, one in the blue phase, 0.4, one in the red phase, 0.1. And let's say that I don't know this. I model the signal as an Ornstein-Uhlenbeck. So I estimate an Ornstein-Uhlenbeck on the entire signal. Okay, so I simulate it according to this heterogeneous asymmetric model. But then I don't know this. The user doesn't know this. They use their good old Ornstein-Uhlenbeck model. So if you estimate an Ornstein-Uhlenbeck process on this path, then of course you're going to estimate some parameters, and you're going to estimate that the mean perversion of this entire path is 0.27, which is between, it's like an average of the two phases, it's between 0.1 and 0.4. So it means that if you ignore this asymmetry, which we do see in the data, there's a lot of asymmetry between what happens near 0 and far from 0. If we ignore this asymmetry and we just estimate classical OU model, then we're going to overestimate the mean reversion in the down phase, and we're going to underestimate the mean reversion in the up phase. And we also overestimate the volatility if the volatilities are different, which is the case here. I'm going to overestimate the volatility in the down phase, underestimate it in the up phase. So, and because the strategy is very asymmetric, because you don't hold the stock in the up phase, you only hold it during the down phase in the strategy. So in fact, you're going to underestimate both the volatility and overestimate the mean reversion. So you're going to actually only at the time when you care is the one of the two phases. So that's why it makes sense to model the dynamics in the two phases differently. I don't care about what happens in the plus phase because I don't hold the stock here. I do care about what happens in the minus phase because that's where I short the stock. And so it means that I'm going to have the wrong parameters for my risk and return estimation because mean reversion determines the return, the gamma, the volatility determines the risk. I'm going to have both of them either too small or too big. So this shows that if I ignore the asymmetry, that's why maybe I get these very incorrect representations of the amplitudes and the durations of the excursions, because I'm trying to fit one parameter or two parameters into the entire sample, whereas in fact, the strategy only cares about one part of the excursions, and I'm not representing that correctly. So this kind of model construction actually follows closely the decomposition of the profit and loss of the excursion, because it fits a model exactly to the features of the process that we're interested in, and those are this decomposition in delta excursions. Any question about this construction? So
no questions in the chat.
Oh, okay. I don't see the chat.
There are no questions in the chat.
Okay, so this construction I gave is an example. Of course, there's no obligation to use Ornstein-Uhlenbeck as building blocks. You can build blocks with anything, but of course, if you want the model to be tractable, you should use building blocks which are easy to simulate or compute with. Therefore, because the transition probabilities of X will be determined by the transition probabilities of S plus and S minus. So as long as I have a model with explicit transition probabilities for S plus and S minus, the building blocks, then I can simulate them, or I can compute with them whatever I want, even though X is very complicated, asymmetric excursions, non-Markov, whatever, it doesn't matter, because every computation or simulation is split into steps which involve only the building blocks S plus and S minus. And of course, you can also use as S plus and S minus non-Markov processes, but then, okay, then the whole thing will not be Markov, but you can build your delta excursions with other ways than Markov processes and paste them together, but then the whole thing is not Markov. Here in this construction, the global construction is still a Markov process, but on a large state space, and you inherit the Markov property of the components by just adding one more variable, which is the regime. You can also do the same construction with more than two regimes. So here I have two regimes, but there's no problem with adding more regimes. I can have any finite number of regimes I want, and I can associate the regimes with hitting times at different levels. Let's say that I want to involve a stop loss level or a limit on the positions. If the limit on positions is reached, then I do something else. I can include two levels. I can include upward and downward hitting times. So this will just increase the number of regimes and increase the number of building blocks, but the construction is fundamentally the same. So I just give the construction here for two, but you can easily imagine that this construction can be done in general for more than two regimes. And it may be interesting from a mathematical perspective. For the delta excursion applications, I only need two, because delta excursion by definition is composed of two parts, the up and down part. But from a mathematical point of view, you can do this construction with n regimes, and then you need S1, S2, Sn, and you just augment your state space by adding a second component, which can take n finite values. Everything else is exactly the same. But then you don't interpret these EK as delta excursions, but you interpret them as some building block that you paste together. Okay, so this can be interesting for construction of processes. And when is this interesting? Well, I just said a word about that. So I can write a stochastic differential equation, in fact, for X. What will be the stochastic differential equation? Well, the stochastic differential equation will be dx equals, well, ds plus times an indicator showing me I'm in the plus phase, plus ds minus times an indicator or showing me I'm in the minus phase. So ds plus and ds minus, if they're Ornstein-Uhlenbeck's or some diffusions, they have a Ito differential. So the indicators will be exactly the indicators of these up and down phases. So indicator of theta plus k, tau plus k, and then for the other one is the other way around. So I can write it always in an Ito differential form. This shows me that this is going to be an Ito. If S plus and S minus are diffusions, then X is going to be an Ito process. But this construction, what is not nice is that the coefficients, the characteristics of the Ito process will involve these indicators. So you have discontinuous characteristics, which is not nice. So in general, there's no general theorem showing that you have a unique solution if you have these nasty indicators of stopping times in the coefficient. So if you try to construct this process directly with either an SD approach or as an Ito process, you have these discontinuities which are nasty, and the discontinuities happen exactly at these orange points at the boundary. But instead of doing it like that, what we say is that, well, there's a nicer way of doing it, is that if I lift it to this bigger space, then it's discontinuous if I view it as a function on R. But if I view it as a function on the bigger space, there is no discontinuity. It's just that I take the two green and blue parts and I paste them together in a way that the whole thing is nice and well behaved on the bigger space. So it's just a way of, you can think of this as a way of constructing processes with discontinuous coefficients or discontinuous characteristics. And in fact, this is the point of view that was developed by Watanabe in his work in the 90s. So he used Ito's theory of excursions not to study the excursions of certain stochastic processes. That was the point of view developed by a lot of other people. But what Watanabe immediately recognized the potential of this excursion theory as a way of constructing processes with nasty coefficients, which have discontinuities on some boundaries and so on. So instead of looking at the coefficients and trying to prove directly the existence of solutions, you look at all the points where the coefficients are not well behaved, discontinuous, or the derivatives are discontinuous, so on, and then you transform them into the boundary of some state space, and then you construct the processes as a pasting of excursions on that state space. So this is a trick, which is a very nice approach that was used by Watanabe for proving the existence of a certain diffusion processes with boundary conditions which are irregular. And here you can think of it as a simple example of that kind of approach. But I'm just saying this is a very useful thing, not just for this application, but from a mathematical perspective, for constructing processes which live on a space with boundary and whose coefficients may be irregular on the boundary. And that's in general, it's a technically challenging construction, but with excursion, you can actually go around that in some cases. Okay, any questions about this? So if not, maybe it's a good time for a break, and then after the break, I'll talk about the non-parametric approach to this. Okay. So we saw in the first part Markovian construction of processes with given properties for their excursion. So basically, I want to construct a process whose delta excursions have certain property, and even I can specify it in more detail. I may want the upward phase to have some property, the downward phase to have another description. And what I showed is that if these building blocks are Markov processes, then I can paste them together and get a process with a desired decomposition in delta excursions. And more specifically, I can build a process with a given distribution of delta excursions. So this is a way of constructing the probability measure pi delta on the space of delta excursions, and then you generate ID copies from it and paste them together. And in this construction, we have explicitly the infinitesimal description is still infinitesimal because we have the explicit description of the process in terms of its generator, and we also have the description of the process in terms of its transition probabilities because we still have access to the transition probability. So it's a Markovian construction. Now, but this is a theoretical construction, so I need to give you two SDs or two Markov processes, then you paste them together, and then you get a new process. Now, in the applications that we considered before, we don't have a Markov process to start with, we have data. And the data, as we saw, can be quite complicated. I mean, they have, you can try to fit a diffusion model to them, but as we saw, no classical diffusion model gave you really the right properties that you want. So in this last part, I'm going to describe a more flexible approach that doesn't need to have a specific functional form for the transitions or the SDs, or no infinitesimal description is required, but you need data. So this is what I call the non-parametric approach to modeling of excursions. So remember that when we did the decomposition of a path into delta excursions, so this is a pathwise decomposition. It has nothing to do with the probabilistic assumptions on the path. And what we saw is that these delta excursions in the Markov case, there are IID. And in general, you know, even if the process is not Markov, but if it's ergodic, you know, you will have infinitely many delta excursions. It goes back to 0 from delta infinitely many times. So you have a sequence of delta excursions that you can obtain from the path by doing this decomposition. So give me a path and I slice it into delta excursion. Now I have a sequence of delta excursions. And the description, Ito's description, describes these delta excursions through their distribution pi delta on the space of excursions. So this we can do it with any process, with any path. I'll always get the sequence. If it's Markov, then it'll be ID sequence. If it's not Markov, then it'll be still a random sequence in the space of delta excursions with some law. Now, starting with a sequence, this is, I can think of it as a sample. How many elements I do have in my sample? What's the sample size? Well, we call d delta t the number of delta excursions of the process up to time t. This is the counting process we introduced in the beginning. It corresponds to the number of transactions in our strategy. So if I have observed the process over time t, I have a sample of size d delta t of delta excursions. And so the idea is, well, using this sample, I'm going to estimate the distribution. How am I going to estimate the distribution? Well, the simplest thing you can do if you have a sample is you look at the empirical distribution. So I'm going to construct a probability measure, which I call pi t. So pi superscript delta, this is the underlying distribution of delta excursions generated by S. But pi t is another object. It's just the empirical distribution of delta excursions. It just puts a point mass at each delta excursions I already observed. So this defines a probability measure on the space of delta excursions, which is a discrete measure. And I normalize by the total number of observations. This is the total number of delta excursions up to time t. So this is a probability measure called the empirical delta excursion measure. No assumption here on S. S can be a single path. It can be a Markov process. It can be whatever you like. I can always build this from any path. Okay, so this decomposition exists, and I can always build this. I call this the empirical delta excursion measure associated with the path S. Now, if S is a Markov process, then we know that these elements are IID. So this is an empirical distribution of IID sequence, and we know a lot about this. The law of large numbers says that this empirical distribution will converge to pi delta, the true distribution, and more specifically, the convergence of the empirical distribution to the true distribution is the Glivenko-Cantelli theorem. So it tells you that, yeah, this is going to be a good estimator for the unknown distribution of delta excursions, which you want to estimate or model. But this Glivenko-Cantelli theorem, the law of large numbers, as you know, holds more generally than for IID. In fact, if S is ergodic, that's enough. If S is ergodic and recurrent at 0, it just is, in particular, the only thing I need is that it goes back from 0 to delta in a finite time. Then if I wait long enough, I'm going to have a larger and larger sample of delta excursion. So it means that d delta t will go to infinity as t goes to infinity. So if I have a long observation period, then I will eventually get a good approximation of the distribution of delta excursions. So this empirical measure, even in the not just the Markov case, but the ergodic case, this will converge to pi delta in a certain sense that I can specify. So, and this is important because, as you saw, many of the examples we considered in the first lectures were fractional processes. So we look at the fractional Ornstein-Uhlenbeck model, which is used for volatility and so on. So these are not Markov processes, but they are ergodic, and they're known to have ergodic properties, the recurrent properties, and so on. So these processes fall into this class, but they're not Markov. So this construction here, this approach, is more general than the previous one. I don't need Markov processes as building blocks. The data can be Markov or non-Markov. This thing is always well defined, and if it's ergodic, then this will converge to a certain object as I have more and more observation. And this object is going to be the distribution of delta excursions of my process.
Excuse me, Rama, I forgot to tell you that during the break there were 2 questions. I don't know if it makes sense to answer them now or later.
I don't see them. Where are they?
Can you open the chat, or do you want me to?
Yes, let me see if I can open the chat. Oh yeah, chat 8. So Russia crisis, is this the question?
Yes, this and the next one.
Yes, who is asking the question, if I may ask? I don't see the name.
I think he's Bouvier, perhaps.
Okay, anyway, so what do the time series tell us about OU? Well, the time series do not tell us anything about OU because they're not OU. I don't know what this means. So are you saying that I think you're saying that in the Russia crisis, this is the example I gave you yesterday, the problem in the Russia crisis was that spreads, which were usually mean reverting, credit spreads, which were mean reverting previously, all of a sudden stopped mean reverting to zero, and they diverged from zero for a long time. So the losses of funds like LTCM were precisely associated with a long excursion away from the zero of a variable which they bet on being a mean reverting variable. So the speed is a function of the state of other factors. Yeah, probably, but so this, I mean, for example, in the construction I gave in the first part, you can include other variables. I included a regime plus minus, but you can include another variable. And you could say, as a function of some other variable, the mean reversion will slow up or slow down. That's an alternative way to construct. And it will give you asymmetric excursions. Yeah. So I'm not sure if I answered the question. No, that's other question. No. Okay. So okay. So here, the point is that this new construction, I don't need anything to be in Markov. I need things to be ergodic. So as time increases, as the observation period increases, I get more and more samples of delta excursions. And then I can have a law of large numbers or an ergodic theorem, which then tells me that this sample distribution will converge to the distribution of delta excursions pi delta. So, so the idea is this: I construct this empirical distribution, and then what you want to do with this? Well, ultimately, I want to construct a process. What does it mean? It means that in financial applications, for example, I need to be able to simulate this process, simulate paths. How do I simulate paths only knowing this pi t? Well, I can do the following. This is what we call a non-parametric scenario simulation. So again, the idea is I use this decomposition in delta excursions, but as a construction method. So we call this non-parametric scenario simulation by pasting of delta excursions. So I start with my data, sample path S. I decompose S into delta excursions. So this is the unique decomposition of any continuous path into delta excursions that we saw earlier. This will give us, how do I do this decomposition? This is what we saw in lecture 1. You define these hitting times, 0 and delta. Every time you hit delta then 0, you slice it. This is E1, then E2, and so on. So it's just slicing the path. It's like slicing this path into the red and blue pieces. Okay, so I take my path, this is my sample path, I slice it into red and blue, and now I take these pieces, these are the pieces of my decomposition. Okay, so this is the data. Now, so I have n delta excursions from my path, and now this gives me an empirical distribution. What does it mean to sample a path from this empirical distribution? It means that I'm going to basically shuffle these delta excursions. Every time I'm going to pick one of them at random, and then I'm going to add it in my path, and then I'm going to pick another one at random. I'm going to concatenate, paste them at 0, and then a third one, and so on. So this is equivalent to the generating ID sequence of integers, K1, K2, so on. And then I apply first the delta, I follow first the delta excursion K1, then K2, then K3, and then I paste them together. So this leads to a construction of a path by concatenation of these excursions in the order given by my random sample. And this gives me a non-parametric way to generate scenarios. But by construction, these paths will have the correct distribution of amplitudes for the delta excursion. They will have the correct distribution for the duration of the delta excursion because I'm using the actual delta excursions from the data. So since we saw that in the trading strategies, what we're interested in, the return and the risk is only sensitive to the distribution of durations and the distribution of amplitudes, by construction, this method will give me the correct metrics for the risk and return of these strategies, because the risk and return of strategies is a sum over quantities that depend on one delta excursion and one delta excursion only, and they involve the height and the duration of this delta excursion. And by construction, this pasting method conserves both quantities by construction. So this gives me as output simulated sample path that I can use to test the performance of strategies, and this sample path is guaranteed to give me the correct distributions for the height and the duration. So for instance, if I look at the graph like this, the number of level crossings, the number of delta excursions in a period t, the realized profit, delta d, delta t, they will give me exactly the correct graphs, the same as in the data if I do it in the stimulated path according to this, because I preserve exactly these quantities. So in fact, they'll give me exactly the same graphs as in the data, because the quantity d delta t is conserved. Okay, it's not a large number telling me for large t I converge. It is for any t I will get exactly the same graph. So this guarantees that I'm not distorting the properties of the data. At least these two properties are conserved. So here's an example generated from the Coca-Cola Pepsi trading signal. So what do I do here? I take my 10 years of data for this signal, and then I slice each day into delta excursions. And then here is an example of a sample path for one day, but generated using this nonparametric method. I pick, in this case, there are 3 delta excursions picked from the historical data. So each of these delta excursions is a piece of the path actually followed by the signal, but this scenario over one day doesn't exist in my signal. It was obtained by pasting together 3 delta excursions from 3 different days. And in fact, I can also paste the blue and the red parts independently. So there are many ways you can do this. So this path corresponds to delta excursions having the realistic features as observed in my signal. For example, you see that there is a lot of asymmetry in the up phase and the down phase. So here we have up phase, you have a huge volatility and a different type of behavior than in the down phase. This is something we see in the data, very difficult to model analytically. The nonparametric method gets you for free. Okay, so that's the benefit of the nonparametric method. The features, including height and duration distribution of the delta excursions, are conserved. And what we also know is that if the process S is Markov, then, well, this construction gives you a process with the same law as S, because then these are IID, and when I shuffle them, I'm not changing the law of the IID sequence. So this construction will give me back the X will have the same law as S. So we have a construction which preserves the height and the duration distribution, and for which Markov processes are a fixed point. So if I start from the law of a Markov process, I do this procedure, I get back the same law. If it's S is not a Markov process, then in general, the law of X and S are different. But the law of the joint law of the height and duration of the delta excursions is the same. So if the quantities I'm interested in only depend on this, it's fine. I'm fine. I don't need to worry. But if I'm interested in other path-dependent quantities, they may be different. The case where X and S have the same law exactly are, well, it's the special case is a strong Markov process, but more generally, if the law of the sequence of delta excursions is exchangeable, not IID, but exchangeable it is enough, then X and S have the same law. What are these processes for which the delta excursions are exchangeable but not IID? Well, they are called generative processes or something like that. So it's these are a class of processes studied in queuing theory and mathematical biology. They are processes such that at each hitting time, the process is regenerated, or at certain hitting times, but not necessarily IID. For example, if you take a renewal process, you take a renewal process, or take a counting process whose inter-arrival times are non-exponential. It is not Markov, but it's of this type. So the delta excursions will still be exchangeable, although they're not independent. They're not IID. So, but in general, the point is that for the applications we're interested in, we don't really need to conserve the law of the process, but we need to conserve some properties of the delta excursions, and this procedure does it. But this procedure is completely non-parametric, so it's a more flexible thing. You can apply to data which can be very complicated, not modelable easily with a diffusion. Well, that doesn't matter. Okay. So any questions about this? Now, I think here there are many interesting open questions which we are actually studying right now with my co-authors. One is, well, if you do this, what do you get? What kind of process is this? So we said that if S is Markov, then X is the same as S. But if S is not Markov, for example, if S is, say, a fractional Ornstein-Uhlenbeck, a very complicated process, well, it's still ergodic. You can do this. What is X? So X seems to be some shuffle. So it's like some kind of averaging of S, because you take the excursions, you shuffle them, and then you follow them in a random order. So it's clear that it's clear, I think, that you will not preserve the law of S, but you get something which has the same, so the paths of X and S, very importantly, have the same roughness, because by construction, you follow the pieces of the paths of it. So if S has a certain roughness, you preserve that. You preserve the properties of the delta excursion. So you preserve a lot of things, but you don't preserve, if there's a memory in the path of S, in the dynamics of S, you may not preserve the memory, at least beyond one excursion. So S and X may, in that case, if S is not Markov, then X it's not easy to relate them together, but we'll still know that they have some properties in common. What is X? If S is a semi-martingale, for example, is X a semi-martingale? If yes, can we relate the decomposition? This construction leads to some interesting questions, and and some of them are relevant for applications. Some of them are of a theoretical interest. The second question, which has been studied a little bit by the Japanese school following Ito's early work, is if you look at this construction here, you look at a process, and then you look at the empirical distribution of delta excursions. In what sense does this converge to pi delta? And in general, if I do such constructions, so in general, underlying this non-parametric simulation is the construction of pi t. I mean, I don't speak about pi t in this simulation, but what I'm doing here is I'm simulating from pi t and then pasting together. So if you look at this construction of Watanabe, who constructs processes from excursions, basically, if you have a sequence pi n of probability measures on the space of excursions, if pi n converges to a limit, which is a probability measure on the space of excursions, what can you say about the law of the processes built in this way? Okay, so I sample from these delta excursions, I sum them together. Can I say, for example, that if the law of the delta excursions converges to some limit, then the law of the process I'm constructing converges to the law of some limit process whose excursions are described by the limit pi? If yes, in what sense does it converge? Is it weak convergence? Is it some other type of convergence? So these are some questions that have been partially studied for the Markov case in some examples, but in general they are open questions for the general case, and they're certainly they have not been studied in the cases beyond Markov. But as I tried to explain, this construction makes sense beyond Markov for an ergodic process. So it is interesting to see what does that mean, in what sense do these things converge, and what do we get as the limit? Okay, so the only thing that we're saying here is that what we get is a process which has some nice properties for excursions and does what we want, preserves the height and duration distribution. But beyond that, I'm not giving you an infinitesimal description of X. And I think that's the kind of a theoretical question which might be interesting. Can I, if I know the infinitesimal description of S, can I give an infinitesimal description of X? Okay. So those are some open questions. And I think this is a rich theory in general to look at, both from the perspective of theory and application. So to summarize, what I try to convince you in these lectures is that looking at the modeling of price processes or trading signals through the lens of excursions can be very useful and fruitful because many properties of dynamic trading strategies are in fact completely determined by excursions of the underlying trading signal. We introduced the concept of delta excursions, which captures exactly what are the properties of the path that contribute to the realized profit, drawdown, risk, maximum loss, number of trades of these strategies. So we showed that if you know everything about the delta excursions of the signal, then you know everything about the strategy. And then how do we learn about the delta excursions of the signal? Then we showed that there's some results that you can derive pathwise using the roughness properties of the path without any further assumption on the probabilistic properties of the signal. Then we showed you a second class of results, which were under the stronger assumption that the signal is a Markov process. And there we have the very powerful tool of Ito's theory of excursions that completely describes everything in terms of a single object, the Ito excursion measure, or a distribution on the space of delta excursions, if you want. And I try to argue through all these examples that what we want to model for these applications is really the properties of delta excursions rather than infinitesimal description of the process or transition probabilities at fixed times, say daily returns or hourly returns, things like that, which are the traditional focus of econometric modeling. Okay, and I showed you examples where we have well-known diffusion models that you use a lot for these applications. They seem to do a poor job in modeling the properties of delta excursions that we're interested in. So then the last part was, okay, what can we do other than use OU? I showed you two approaches to build new models which capture the desired properties of excursions for your data. One was these parametric models use simple parametric models such as OU or Brownian motion as building blocks and do this pasting operation. This leads to an analytically explicit class of models which can have asymmetric excursions, your favorite distribution of heights or durations. So that's one approach, which is still very analytical. And then a second non-parametric approach, which leads itself to easy simulation and makes very few assumptions on the data. In fact, the only assumption is really ergodicity. And both approaches can be useful for the applications we described in the first lectures. So that ends my lectures. There's a paper where you can find some details on these constructions and examples I gave, and more details on the proofs of the mathematical results, and I'm happy to take questions.
Some questions, comments?